Math 2 students, this is Miss Van Vickle, and this is the half-life problem from Tuesday that I promised to work for you. This is a series of lectures designed to keep you up to speed while I'm out of town, and they're designed to be lectures that I would have given on Wednesday, April 22nd. And the first problem I'm going to work for you in the lecture series is from yesterday's notes, and it's problem number 4 at the very bottom of your notes page. And it says potassium 42 is used as a tracer of potassium distribution in body fluid compartments and in localization of brain tumors. The half-life of potassium 42 is 12.4 hours, and it wants us to write an exponential function to model the amount of potassium after X number of hours. So what I'm going to do is I'm going to say y is equal to, let me get my camera over here where you can see what I'm writing. Y is equal to the amount that I start with, A, and we are half-lifing, so the amount remaining in the body is 1/2 of what we started with, and that happens after 12.4 hours. So we would write X over 12.4. Now let's take a look at why we put 12.4 here. The reason is if I put in 12.4 for the number of hours, we would want to have made a half-life once. So when I put 12.4 in for X, the exponent resolves to 1, and that would have the effect of me multiplying my initial value times 1/2 once. So when we deal with half-life, we always divide the number of hours by the half-life, or minutes if the problem's given in minutes. So this is the function that we want to use to model our half-life situation. Part B says how much of an 848 gram sample of potassium 42 will be left after 3 hours. So now it gives us our initial value of 848. So we just insert that into the equation. The amount left is equal to 848 times 1/2, and it says after 3 hours, so to the 3 over 12.4 power. And so the way I would choose to solve that is to put it into my calculator, and so that I get order of operations done right, I'm going to say that I have 1/2, you can put in 0.5 if you'd like to, and I'm going to raise that to the 3 divided by 12.4. Always remember, your fractions have to be in parentheses. And so that gives me my half-life, but the problem said we started with 848 grams. So I have to take that and multiply it times my initial value. And notice I have 717 grams remaining after that period of time. Let me move this down so you can see what my keystrokes look like. 1/2 raised to the 3 divided by 12.4 power. I've put all my fractions in parentheses. And I went ahead and hit enter, and then I multiplied the result of that times 848 to get my 717. So that's the answer to part B. I have 717 grams of potassium 42 left, and we should include units with that. Then it says how much of an 848 gram sample of potassium 42 will be left after 62 hours. So the process for working this part of the problem is just the same, except the value for t is different. It's 62 over 12.4. So let's use our calculator to figure that out. And this time I'll use 0.5 to the 62 divided by 12.4 power. And then I multiply that times 848. And I get 26.5. So there's my answer to part C. And then it says, after how many hours can you expect less than 10 grams of potassium 42? And in this case, I am being asked to solve for a time period. So I have 848 times 1/2, and in my exponent I have x divided by 12.4. And again, I don't have any handy way of solving for a variable up in the exponent. And so what I'm going to do is I'm going to use my calculator. And historically I've been dividing both sides by 848, or by the amount, to isolate this term. So I'm going to go ahead and be consistent and do that again. And on the left side I get 10 divided by 848. So let's put this into our calculator. Let me get this over here so you can see what I'm doing. I'm just going to put 10 divided by 848 in for y1. And I'm going to let the calculator sort out that arithmetic. And then I'm going to say y2 is equal to 0.5, or 1/2, raised to the x divided by 12.4 power. And again, I've got to have my fractions in parentheses. And I graph this, and I'm looking at really small numbers here. 10 divided by 848. My numerator is small, my denominator is really big. So I'm going to go to my window, and I'm going to say, maybe this will do. Maybe the -1 and the +1 will work. So let's see what happens, and let's see if I can see enough of my graph to tell what's going on. There's my exponential decay curve coming down nicely. But I'm not seeing my line at all, the line represented by the 10 divided by 848. So let's see if I can get my window a little bit smaller. I'm going to do y min of 0.5, and a y max of y min of -0.5, and a y max of 0.5. And let's see if that helps at all. And I'm still not seeing my line. So I may need to choke down all the way to something like 0.1. Now ooh, there's my line. I think I finally got tiny enough that I can see what I need to see. But now if we notice right over here, our x max needs to be increased. So I'm going to go over to x max and make it maybe 100.
Well, hi, Jeff. Hello.
So now I notice that I can see the intersection of my graph, and I do second calc, and I'm looking for an intersection, and I hit enter twice and go down to the point of intersection and hit enter, and I notice that when x is 79.4, I have the y value I was looking for. So the answer to this would be that after 79.4 hours, I would expect less than 10 grams of potassium-42 to be still in existence. So that's it for half-life, guys.